So we hear the word insulin thrown around a lot, but what actually is insulin? Insulin is a hormone produced by mainly our pancreas. However, our brain can actually produce its own insulin. So before we get into what insulin actually does, why do we produce it in the first place? So the body maintains a fairly stable blood glucose level, and as the name implies, this is just the amount of glucose inside the bloodstream. When we wake up in the morning, this is referred to as our fasting glucose, as long as you weren't eating any meals overnight. And a normal fasted glucose is between 70 and 100, but if you're on a lower carbohydrate diet, it could potentially be lower. And an increased level of fatty acids means that and the reason this is important is because the body will actually use the blood glucose, pull it into the cells, and use it as energy. But if we have more free fatty acids, these fatty acids can also be used as energy. The other main fuel would be ketones, and I just released a video about why the body actually creates ketones. But coming back to insulin and blood glucose, insulin works to keep our blood glucose levels between the 70 and 100 milligram per deciliter range. The most common time that we'll release insulin is after a meal. And now the lower carbohydrate and protein this meal is, the lower the insulin release will be. And this is because fatty acids will increase our blood fat levels but not our blood glucose. Protein typically doesn't increase our blood glucose levels. However, if we eat an excess amount of protein, only a certain amount of it can actually be used for muscle protein synthesis, and some of these excess amino acids, which are simply just the building blocks of protein, can be turned into glucose inside of the liver. This process is referred to as gluconeogenesis, and as a result, our blood glucose will elevate. So the specific cell inside of the pancreas that insulin is stored and released from is called the pancreatic beta cell. And our blood, along with the glucose contained inside of our blood, is always flowing through the pancreas. And now inside of these pancreatic beta cells, glucose is turned into ATP. And as most people remember from biology class, ATP is what we use for energy inside of all the cells in our body. And this is why we eat glucose and fatty acids, simply to create this ATP molecule. But these pancreatic beta cells produce ATP in a glucose-dependent manner. What I mean is that the more glucose inside of our bloodstream, the more glucose will be entering the pancreatic beta cells. And the more glucose there is, the more ATP these cells produce. And what happens when we have a buildup of ATP inside the cell is it will actually bind to a specific receptor on the membrane, which is just the outside of the cell, elegantly called an ATP-dependent potassium channel. And when ATP binds to the channel, it will actually cause this channel to close. And typically what this channel will do is allow potassium ions, which are positively charged, to get out of the cell. But when we have excessive ATP production from high blood glucose, this ATP binds and will turn off the channel. This means we have a potassium buildup inside of the pancreatic beta cell. As I mentioned, potassium is a positively charged molecule. So we get a buildup of positively charged molecules inside the cell. And this is also referred to as raising the voltage of the cell. And interestingly, also on the membrane, we have what are called voltage-dependent calcium channels. And as the name might imply, these channels will respond to an increased voltage. But when the voltage of the cell increases, these channels actually open, allowing calcium from the outside of the cell to enter into the pancreatic beta cell. And calcium is also a positively charged molecule. So the first thing that's important to know is that potassium and calcium are extremely important for proper insulin functioning. And now the other thing that calcium does is actually allow for the pancreatic beta cells to release the insulin that are stored inside of them. So insulin gets stored in what are called vesicles, and these are kind of like little envelopes that hold the insulin until our blood glucose elevates. And calcium allows these little envelopes to bind to the surface of the cell and release that insulin into our bloodstream. So in short, the release of insulin starts with elevated blood glucose, causes a potassium buildup inside the cell, then calcium entrance into the cell, and subsequently insulin release into the bloodstream. So now that the insulin is in our bloodstream, it will go around and bind to insulin receptors. These are located in just about every tissue of the body, including the kidney, the liver, and predominantly the muscle tissue and the fat cells. And now we can't give insulin one single function because it does a myriad of different things. So insulin never actually enters into the cell. All it does is bind to a receptor on the surface. And this triggers something kind of like an assembly line of different proteins to begin becoming more active inside of the cell. And the downstream result is the upregulation and downregulation of different enzymes inside of the cell. And it also causes specific proteins inside of the cell called transcription factors to actually bind to the DNA that's housed in every single cell and increase the production of proteins due to increased genetic expression. The best way to think about it is that most of the processes that occur inside of the cell are mediated by proteins, and turning different proteins on or off, or increasing or decreasing the production of proteins, changes the activity of the cell. And this is how most, if not all, hormones and neurotransmitters work. And the proteins that are increased in activity from insulin are proteins responsible for allowing glucose, amino acids, and fatty acids into the cell, and increasing the storage of these molecules, specifically protein synthesis to increase amino acid storage, triglyceride synthesis, which is how we store fatty acids, and glycogen synthesis, which is how we store glucose inside of our muscle, kidney, liver, and brain. And insulin will actually inhibit the release of glucose, fatty acids, and amino acids into the bloodstream. And this is why insulin is often referred to as an anti-catabolic hormone, because it inhibits the cells from breaking down and releasing their stored molecules into the bloodstream. And in this way, insulin will take all of those elevated macromolecules, specifically amino acids, fatty acids, and glucose, inside the bloodstream, and allow them to be stored inside of the cells, which removes them from the bloodstream, which will subsequently return our blood glucose, blood amino acids, and blood fatty acids to normal levels, given that your insulin signaling and response is normal. And I'll film a video about improper insulin signaling and response in the future. And now insulin does have a few other interesting effects. Insulin can increase the production of satiety-promoting hormones, specifically the hormone leptin. Insulin can also increase the uptake of LDL lipoproteins out of the bloodstream. These are the proteins inside of our blood that carry cholesterol. And sometimes they can become harmful when there are elevated LDL proteins inside the bloodstream not being taken up by the cells. And insulin can increase the cell's uptake of these LDL lipoproteins, supplying the necessary cholesterol for all the cells in our body. Insulin can also increase the production of things like gonadotropin-releasing hormone, which is the hormone produced inside the brain that starts the downstream cascade of sex steroid production, including testosterone, estrogen, and progesterone. Insulin also has some pretty interesting effects in the brain. It can actually increase protein synthesis inside of the brain, and this is important for making new connections and learning. In essence, insulin allows for anabolic processes to occur. Some of these anabolic processes can be extremely important, such as increasing hormone output and increasing protein synthesis. However, increasing insulin extremely high will increase fat storage. And one of the downstream consequences of excessive fat storage is a phenomenon called insulin resistance. And this is because when fat accumulates inside the cell, some of these fat molecules can be converted into molecules that will inhibit all of these proteins involved in insulin signaling, meaning that when insulin binds to its receptor, that assembly line is a little bit out of whack, meaning that we'll have a difficult time increasing protein synthesis and allowing for the cell to actually uptake the glucose from the bloodstream, which could leave our blood glucose levels elevated. And this not only decreases the energy availability of the cells, but chronically elevated blood glucose could actually be quite damaging. And there's a myriad of other impacts of insulin resistance, which I'll try and release a much more in-depth video on in the future. But I hope this video helped clear up a little bit of the confusion as to what this insulin hormone actually is, why we produce it, and what it actually does.